ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. So today what we're going to do, ladies and gents, is we're going to take a look at the post lab. So hopefully you've gone through your density of a metal lab, you've collected your data, and you did everything without making any blunders. And so one of the things that we really wanted to do, and the goal of that lab, even though I know we've measured density and worked with density before in 6th, 7th, and 8th grade, and it keeps kind of popping its head into our classrooms, but it's something that's simple where you don't have to think about what you're measuring or doing, but you can focus on some other techniques that we're trying to get you to learn. And in particular, the goal of all of this was to have confidence and actually record our measurements so that we had confidence in those measurements. And that would be so that anytime we wrote things down, we were confident that we actually read the equipment correctly. And then people that came beyond and past and behind us, when they looked at our measurements, they could also have confidence that we were reading and recording to the proper number of digits. Now remember, with us, all of this really started when we were looking at the equipment, whether or not we were going to be able to identify what the increments were. Because remember, the increments were actually able, when we looked at them and determined what they were able to tell us to what digit we would be able to read a piece of equipment to and be confident about all of those digits, right? And we actually went one step further. Instead of just calling them digits, we actually referred to them in our last lecture as significant figures. Right? And those significant figures represented just those numbers that we have written down from a piece of equipment that we had confidence in. And then those things that we have confidence in led to the precision that we were after, and then that ultimately, that precision allows us to represent how many of those digits we are actually confident about in our measurement. And so now let's take a look at a couple of the pieces of equipment that we used in our lab. All right, so one of the first pieces of equipment that we ran across in the lab was an electronic balance. And so an electronic balance is really easy. I don't know if you can read this very well, but our precision is actually listed on the piece of equipment. And you'll notice our display, this decimal point, which is not very easy to see, but it actually tells us what digit, just the display itself. So this would always be recorded as 76.59. And then grams, our units are listed up here in the top left-hand corner of this particular scale. Right? So anything that was written down from this reading other than 76.59 would be the type of error called a blunder, and we wouldn't have written down and recorded the proper number of digits. So our sig figs would be off, our precision would be off, and then everything that we use this in calculations with afterwards would also have some fatal flaws in it. The next piece of equipment that we ran across in the lab and we used it for that water displacement, right? Where we put took an initial reading of volume on the graduated cylinder, we put a substance in, the volume increased, and then we could actually figure out the volume of that substance by taking the difference between what the volume of the water originally was versus what it was after we put that substance in. And so this was a 100 mil graduated cylinder, and what I've got here on the right-hand side, so on the left I'm showing the cylinder, and on the right-hand side, I've just got two different readings that are actually blown up so that we can look and see these. Now I know it's a little bit hard, so I'm gonna go and draw lines in here, right, so that we can actually see where all of these increments are at, and I'll draw it up until the point to where we can actually take our reading right there, right? And so I'll put the meniscus, I'll go ahead and draw it in there in blue. There it is. And so in this particular case, we can see that this marking right here is actually labeled 50, and this marking right here is actually labeled at 40. And so if I count there, I can check and see that my increments here are 1 milliliter. Well, what that means is, like say for example, I was trying to figure out, there's two markings right here. If my meniscus was somewhere in between them right here, I could actually estimate that, and we'd say what, that's 55, 56, 57, 58. So this would be 58 and this would be 59. So if my meniscus was part way in between there, I could actually estimate to that decimal place and say it was like 59.5. So in this particular case, I see that my meniscus is somewhere between 51 and 52. So I'm going to go probably reading off of this, and I'm going to say 52.8 milliliters. And so I would record this as 52.8 milliliters. And again, if I wrote down anything else, if I wrote 52 or I wrote 53, right, those would be blunders. Now, a lot of kids get kind of confused with this because they say, all right, well, Mr. Doolin, what if it was exactly on 40? What if my meniscus was exactly on 40? Would it be appropriate if it was exactly on 40 to write 40, or would I have to write 40.0? Well, you would have to write 40.0. I couldn't just write 40 because given the increments on this particular piece of equipment, I can, with some confidence, actually estimate to that tenths position, which means every single reading that I have to take with this piece of equipment, I would be able to estimate and I would record a digit in that tenths place. And that's why we're looking at increments right when you pick up a piece of equipment are so important, because wherever you can estimate to, that tells you where you're going to have to record and what decimal and what digit you're going to have to record every single measurement that you take with that particular piece of equipment. So let's jump over to the other side. I'm going to go ahead and mark, this is that 50 mark right here, and then there's 51, 52, and then down below I've got 49, 48, 47, 46, and 45 is right there. 44, 43, 42, 41, and then here's 40. And so I knew it was ones. I guess I jumped the gun on that, but I know that there was 10 markings between the 40 and the 50, which means my increments are 1. So now in this particular case, I'll go ahead and I'll put the meniscus in 1. The bottom of the meniscus, I'm reading right there, right? So it's somewhere, what that's 45, 46, 47, 48. It's somewhere between 48 and 49. And again, I'm going to say that this is a little bit more than halfway, so I'm going to say 48.6 milliliters. And notice again, I'm recording to that tenths position because that's where I am allowed to estimate and where I can, with some confidence, estimate to that position. All right? Now, something that's going to come up later, I want to go ahead and point out now, there's bubbles in this graduated cylinder. And I want you to think about how having bubbles inside of that liquid, that volume that you're trying to record, how that would actually introduce errors in and of itself, because that's part of your error analysis on this lab as well. And so think about if I took that bubble away, what would happen to that meniscus? Would it go up or would it go down? And that'll kind of tell you and indicate to you what's going to happen and what kind of error is going to be introduced with our readings if we have bubbles present. The opposite would that be, over here you can see if you're looking at the graduated cylinder, I've got some splashing that has happened, right? I've got some liquid that's up on the side of the container and not necessarily down here with all of the other liquids. So if these droplets, after I started reading everything, if those droplets were to fall down into that liquid, how would that affect all of my readings from that point on? So you have to really kind of think about those two, and that's part of our error analysis in this lab as well. All right, so now what we want to do, ladies and gents, is we're going to start looking at graphing our data, right? And so all I've done is sketched a graph, and if you want to know what my increments are going to be here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 is the scale of my y-axis. And then my x-axis, I'm going to go 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100, right? Now, if I'm going to go ahead and write this, and this data actually comes from data table A, I believe is where I got this data from. And I was able to extract what my volume of each metal was, and I remember I'm looking at cup 1, and then we had the metal from cup 1 and cup 2, and then we had the metal from cups 1 and 2 and 3 was the way that we did this particular lab. And so writing their masses in there, this is going to be 23.79 for me, this is going to be 54.39 for me, and this would be 76.49. My volume readings would be 3.6, 7.8, and then 10.7. And now here's a question. Is your data going to be different than mine? And the answer is absolutely yes, your data is going to be different than mine, right? You performed your own lab. We were kind of willy-nilly playing with putting a third and a third and a third. And so yours will be different, but you can follow along with my calculations what I'm doing, right? So this whole thing was to determine the density of a metal. Well, remember, density of anything is equal to the mass divided by the volume. And so if we think about this and kind of what we know about graphs, I'm going to go ahead and put mass on my y-axis, and I'm going to put volume on my x-axis. And then I want you to think about, pause this video and think, why did I put mass? Why did I choose to put mass on the y and volume on the x? Well, guess what? We understand just from general algebra that the slope of any line is actually equal to y over x, a change in y over a change in x. And so if we look at the slope of this, do understand that the slope is going to be mass over volume. And so what did we just do there? We came up with a graphical way to get density out of our data, right? Because if slope of any line, of any straight line that we put on this is mass divided by volume, that means the slope of any line that we create in this graph, as long as it's a straight line, will be the density, right? So what I'm going to do is I'm going to go ahead and graph my data on here. And so I've got my lines or my data points shown there, and now I'm just going to hand draw a trend line. I'm going to hand draw a best fit line, and it doesn't have to be exact. And I think in your lab I asked you, you know what, just kind of cheat on this a little bit and make the data points run through the first and the third data point, right? So that we can use them, because we're going to use point slope form to actually calculate the slope of the line, and which give us our average density. And so there's a couple of things I do want to touch on before we go past this point as well. If you look here, right, if you look in cup 1, I had some metal in there, and then we took a mass and a volume of that metal. And then in cup 1 and 2, we actually just have more of the same metal. And then in cup 1, 2, and 3, we have the most of the same metal. So all we were doing as we were adding metal to those cups, we were actually just increasing the amount of metal that I was measuring at that particular point. So one thing I want you to understand, the mass is constantly going up, right? And I won't draw an arrow there because it's actually going up as it goes down the table there, right? But mass is going up as we add more and more metal, but also the volume is going up as we add more and more metal. And then one thing that we understand and that we should remember from our lecture is that no matter what these values are, the density of that metal should remain constant, right? It should be constant, which means the trend line that I'm showing here should mimic and mirror what density is, right? The slope of a straight line is constant and the density of a substance is constant. So the slope of this line should also be constant. And I know at this point some of y'all are thinking, Mr. Dillon, what the heck? I could just take the average of those 3 data points and I could come up with the average density. Why do I have to go through this really difficult sounding thing you're having me do right here of graphing all this data and doing trend lines, and then we're gonna have to figure out use point slope form and pull back some algebra knowledge and figure out the slope. I mean, I can calculate the average of 3 points. And that's true. But I want you to understand what we're doing here for you is we're actually teaching you how to do this kind of data analysis, because what if you had 1,000 points or you had 500,000 points? Right? You don't want to calculate the average of 500,000 data points, right? You could actually do this and calculate it and have it run its trend line and regression system in a graphing calculator, and it could actually pick up your trend line and come up with your slope of your line automatically, right? And so now what I'm going to do with you, ladies and gents, is I'm actually going to go through using point slope form, and I'm going to try and do that down here on the bottom so that we can keep everything in one spot. So remember, point slope form was going to be y2 minus y1 is equal to the slope of a line, and then x2 minus x1. All right, and so if we solve this out, because this is really what we're after, and so I'm going to divide off x2 minus x1, and then I'll do it to the other side, right? Because as long as you do it to one side and you do it to the other, we keep our equation relative to each side, right? So that cancels out, and so now all of a sudden I'm left with y2 minus y1 over x2 minus x1 is equal to my slope. And now I'm going to plug in, I'll go ahead and change pen colors here. I'm going to plug in my values here. And I'm going to cheat. I'm going to use the first and third points. Because again, when I had you draw your graph and your data, I asked you to make sure that your trend line ran through those 2 data points. And this is what I was looking for, and this is why I did it. So we would at least have 2 data points on that line. So I've got in my data 76.49 minus 23.79 over, this would be 10.7 minus 3.6. That's actually going to equal, once you do the math on this is going to be 52.7 over 7.1, which is going to give us an average density of 7.4. And the units on this would be grams per milliliter, right? And we understand earlier, right, this is m. This is our slope, and our slope equals our density, right? So 7.4 grams per milliliter is our average density based on this trend line regression. Now, believe it or not, if you used my data and you actually did the density of data point 1, the density of data point 2, and the density of data point 3, and then took an average, it's going to be a little bit different than what we're getting right here. And it kind of is part of just the different ways to analyze things, and I believe the graphical representation and using the trend line regression on this would actually be more effective if we had a larger set of data points. But based on this information, now that I have a density, I have a choice between, in your lab analysis, you were given the density of copper, which is your known value. You were given the density of zinc and the density of aluminum. And our density is closest to, or I guess my density is closest to zinc, and so I would call my sample a zinc metal. And now we have to understand too, ladies and gents, the data points were all relatively close to each other, so my precision was okay here, but my accuracy is just a little bit off, and we start to think back about things like, oh, well, there were bubbles in the graduated cylinder, there were some things that had splashed up on the side. So this is one of those situations where our data was good, we used the proper precision based on our equipment, but there were some errors like the splashing and the bubbles and things like that that introduced enough errors in there so our accuracy was off. So it is possible to have precision without having complete accuracy there. So just wanted to point that out. And that's it, ladies and gents. If you have any other questions, I'll see you in class.